So we're doing the serology chapter here. So to start off, we're going to talk about blood and the composition of blood. When you take blood out of your arm, let's say that you take a needle, stab me in the arm, withdraw blood. The blood that comes out of my arm would be considered whole blood. If you take that blood, stick it in a centrifuge, spin it down, you're going to find that there's different components to the blood. Those components include erythrocytes, which are red blood cells, a buffy coat, which will be your white blood cells and platelets, and the plasma. That'll be the fluid portion of it, of your whole blood. About 45% of your whole blood is considered formed elements. That will include the buffy coat. That will include the buffy coat and the red blood cells. So that'll be white blood cells, platelets, and red blood cells. About 55% of your blood composition should be your whole blood. What we're looking at here would be a hematocrit, and the hematocrit is going to represent the percentage of red blood cells in your whole blood. With physical characteristics and volume of your whole blood, your blood is going to be slightly alkaline. The pH should typically be about 7.35 to 7.45. It's going to have a higher density and viscosity than water. So if I take a drop of blood and drop it into a bottle of water, it sinks. Also, if you get blood in your hand, you feel it, it's slightly more viscous, slightly more oily feeling than water would be. And the normal amount of blood in a male is going to be about 5 to 6 liters, and in a female will be about 4 or 5 liters of blood. What is the function of your blood? What is it here for? Why do we have it? It is going to be a delivery and distribution center. It will be there to help regulate and maintain homeostasis, and it will be there for protection. Delivery and distribution. Gases, nutrients, and hormones and waste, these guys are all present in your blood. So we bring oxygen into our lungs, it dissolves into the blood carries the oxygen to our tissues, dumps off the oxygen, picks up carbon dioxide, brings it back to the lungs, dumps that out. Nutrients, hormones, waste, all the same thing. So we eat food, we absorb the nutrients from the food, bring it over to the liver for processing. After it's processed, we bring it out to all of our tissues and drop off the goods to the tissues. Pick up all the waste, bring the waste to wherever they're going to get processed at. With regulation, it's going to be there for fluid volume, pH, and body temperature. The best thing with body temperature is if it's cold outside and I take a bottle of water and I stick it outside, it's not going to lose its heat automatically. It's not just going to freeze if it's freezing cold out. It takes some time for that to freeze. So since we have fluid in our body, lots of water in our body, in our blood, it helps us to keep our temperature and maintain our proper temperature. And lastly, protection. So we'll have protection against infection and against excessive blood loss. So our white blood cells in our immune system are going to be the main culprit for protection against infection, and then with excessive blood loss, we'll talk about the platelet plug formation. With the blood plasma, it's going to be mostly water. 90% of it's water. Within the rest of it, there's going to be nutrients, gases, hormones, wastes, and proteins. So here we are looking at a slide of blood, of normal blood. These pink looking cells here are our red blood cells, or our erythrocytes. These larger cells with purple in them are our leukocytes, or white blood cells. This would represent a monocyte, a lymphocyte, and here are some neutrophils. And then these little guys, these little purple guys here, these are platelets. So characteristics of a erythrocyte, or red blood cell. They are what's referred to as a biconcave anucleic cell. The reason why they're biconcave is it is there to increase surface area. So if I take a piece of paper and it is 1 foot by 1 foot, that would be considered 1 square foot. If all of a sudden you start giving that paper texture, the surface area of it is no longer 1 square foot, it is greater. So by making this biconcave and giving it a little bit of shape, it gives it a greater surface area. It's going to lack a nucleus, but it'll have most of the other organelles so it can stay alive. Inside of each red blood cell, you're going to have about 300 million hemoglobin. I think the actual number is closer to like 270 or 280 million hemoglobin. Each hemoglobin molecule, which you say here, is going to be made up of a beta 1, beta 2, alpha 1, alpha 2. So it's made up of 4 chains, and each one of these will carry 4 oxygens. There will be 4 iron-containing compounds. Each one carries an oxygen. So each hemoglobin can carry 1 oxygen molecule, or sorry, 4 oxygen molecule. So production of our red blood cells. The process is called hemato or hemapoiesis. That is going to be blood cell formation in general. Production of red blood cells is called erythropoiesis. So hemato or hemapoiesis is formation of blood cells in general. Erythropoiesis, red blood cells specifically. Blood cell formation will occur in the red marrow and is going to be controlled by erythropoietin, which will be released by the kidneys and liver. Erythropoietin is released in response to decreased levels of oxygen. In order for red blood cells to be made properly and efficiently, you're going to need the following dietary requirements. You're going to need iron, because the iron-containing compound. So hemoglobin, heme is in iron, globin is in, it's a globular protein. So we have our iron-containing compounds, and it's a globular protein. You're going to need B12 and folic acid to ensure proper cell division. Proteins, lipids, and carbohydrates, just for the pieces and parts of the cells. After these red blood cells are about 120 days old or so, they get killed off by the macrophage or spleen. Why? Because they don't have a nucleus and they can't divide, and sooner or later they get old. They're just going to need to be gotten rid of. So how does it work? Let's say we get low levels of oxygen. So if we get low levels of oxygen, that is hypo is in decreased, oxia, hypoxia. So that's decreased oxygen. There's decreased amount, this can occur from decreased amount of red blood cells, a decrease of amount of hemoglobin, or decreased amount of oxygen available. Like you move to a higher altitude and the air is thinner. So if you have decreased amounts of oxygen for a longer period of time, or some sort of period of time, sooner or later what happens is the kidneys and liver will start to release erythropoietin. Erythropoietin goes to the red bone marrow of the bones, tells the bones to increase erythropoiesis, and our end product is more red blood cells. Since we have more red blood cells, there's 280 hemoglobin, 280 million hemoglobin inside of each one of these. So each one of these carries a whole ton of oxygen. And what that's going to enable us to do is increase the amount of oxygen we're carrying in our blood. So we increase the amount of oxygen we're carrying. Sooner or later we go to a happy level, and we pass that happy level. So what will happen is we'll tell the kidneys, stop releasing erythropoietin. Alright? Once we stop the release of erythropoietin, we decrease the red blood cell production, and over time red blood cells start to die off, and then our oxygen levels can start dropping again. So it's a teeter-totter type of effect. We call this a negative feedback mechanism. Some erythrocyte disorders, you can have anemias or polycythemias. Anemias are going to be abnormalities of the red blood cells based on the number or shape of them, and polycythemias are going to be when you have too many red blood cells. So here's a nice healthy red blood cell. This red blood cell would be called sickle cell. So this would be sickle cell anemia because the red blood cells are sickle shaping, which is like half moon shaping. Next we're on to white blood cells. White blood cells make up less than 1% of your total blood volume. They do have nuclei, and they are going to be there to provide immunity. They are capable of diapedesis and positive chemotaxis. Diapedesis is the ability of the cell to slip out of the capillary bed, so it can leave the capillaries and go into tissue to go fight stuff off. And positive chemotaxis means that when the cell leaves the capillaries, it can follow this chemical signal to fight off whatever it's looking for. So let's check this out. So let's say this is my blood vessel. If I have a white blood cell here, if it's going to undergo diapedesis, it'll work its way off to the side here. This is called margination. And then what it'll do is it'll wiggle through the blood vessel and leave into the extracellular space, or it'll leave the blood vessel. So here's the red blood cell. It undergoes margination. It's moving towards the wall of the blood vessel. And then the white blood cell leaves the blood vessel. Then it follows chemical signals to fight off its bad guy. So it'll go over this white blood cell, follow chemical signals to come over and fight off the bad guy over here. So we have granulocytes and agranulocytes. We have neutrophils, eosinophils, basophils, lymphocytes, and monocytes. Each one of these will fight very specific microorganisms or foreign invaders into your body, and each one of these are found in very specific quantities within your blood. The normal levels that you'll usually find them in is going to be lots and lots of neutrophils, and you can have a good amount of lymphocytes. After that, there's very few eosinophils, basophils, and monocytes. There's a mnemonic that I usually use to remember this. It's called Never Let My Engine Blow 50-30-530. N is in neutrophil, L is in lymphocyte, M is in monocyte, E is in eosinophil, and B is in basophils. Okay, our formed elements. We're going to have platelets, leukocytes, erythrocytes. We said leukocytes make up less than 1% of our total blood volume, and there's going to be 5 of them, our neutrophils, our eosinophils, basophils, lymphocytes, and monocytes. So here's our ranges. You remember we said never let my engine blow 50-35-30, so like about 50%, about 30%, about 5%, about 3, and about 0. So kind of falls within these ranges. This is the normal range that we'll find these types of white blood cells in. Leukopoiesis, white blood cell formation. Hemocytoblast, right here we have a hemocytoblast. This is going to be like the mother stem cell. This can make any blood cell. From our hemocytoblast, it will differentiate into a myeloid stem cell or a lymphoid stem cell. Myeloid stem cells differentiate into myeloblasts. Myeloblasts will differentiate into promyelocytes or promonocyte. Our promyelocytes make our granular leukocytes, or our granular cells, and our promonocytes make monocytes, and our prolymphocyte makes our lymphocytes, which can differentiate further into a plasma cell. We'll talk about these in the immunity chapter. With leukocyte disorders, you can have stuff such as leukopenias, leukemias, or like Epstein-Barr virus, which is mono. So with a leukopenia, you have abnormally low numbers of white blood cells. With leukemia, you're going to have a clone of a single type of white blood cell that will stay unspecialized, and it's just going to divide out of control. And then with Epstein-Barr virus, or mono, you get tons and tons of agranulocytes. All right, with platelets, hemocytoblast, that's our mother stem cell, can make any other stem cell. They go from there to megakaryocytes, to promegakaryocytes, to megakaryoblast, to promegakaryocytes, to megakaryocytes. Our platelets are cytoplasmic fragments of megakaryocytes. Write that down. Platelets are cytoplasmic fragments of megakaryocytes, and they're going to be critical for the clotting process. So hemostasis. Hemo is in blood, stasis, stopping of or stalling. It's going to be a fast localized response used to reduce the loss of blood through clotting. So let's say that you stab me in the arm and I am bleeding. Not very badly, just a little bit. First, you're going to get vascular spasms. So you're going to get vasospasm. The blood vessel will vasoconstrict. It will close up to decrease blood flow. Next, you get formation of our platelet plug. We'll go through. So the way the formation of the platelet plug is going to happen is we're going to have all these factors, and they're going to meet up with calcium. Okay, all those guys make something called prothrombin activator. Prothrombin activator acts to activate prothrombin. So when prothrombin is activated, it turns into thrombin. Thrombin is going to be used to turn soluble fibrinogen, so this stuff is just dissolved in the blood right now, into insoluble fibrin. So this stuff goes from being dissolved into a like mesh type network. Once this stuff comes out of solution, it forms a fibrin. It'll form a fibrin clot and it'll close up the bleeding, so you stop bleeding. Now let's look at this again. Floating around in your blood right now, you are going to have your PF3 from platelets, you're going to have calcium and other clotting factors. You're going to have prothrombin and you're going to have fibrinogen. When injury occurs, these guys meet up, they form prothrombin activator. That turns prothrombin into thrombin, and then our thrombin will turn soluble fibrinogen into insoluble fibrin, and then we can form our clot and stop the bleeding process. Factors limiting clot growth or formation: you can have anticoagulants such as antithrombin or protein C or heparin. All right, rapidly moving blood. These guys will make it harder to form a clot because the fibrin will have a harder time making a network and it won't be able to stop everything as easily. Some disorders of hemostasis. So we can have a thrombus or an embolus. A thrombus is an anchored clot in an unbroken blood vessel. An embolus is going to float freely. So an embolus can go get trapped in a small blood vessel and it won't let any blood pass on. So imagine an embolus traveling through something large like your aorta, and it goes into a smaller blood vessel until all of a sudden it gets too small and it gets stuck. Once it gets stuck there, no blood can go past it, so that tissue will die because it doesn't have any blood flow. Bleeding disorders. So what happens with bleeding disorders, you can have abnormalities that will prevent blood clot formation, such as thrombocytopenia, hemophilia, some sort of liver dysfunction. So what can happen, the gist of it is you don't make blood clots, you get an injury, you bleed, and you can bleed to death. With thromboembolic disorders, these are going to be people who will be going to like Coumadin clinics. So what happens is they get roughening of the endothelium of their blood vessels, and it'll slow blood flow and stasis, or they can have tons and tons of clots forming, or be more likely to have an embolus or a thrombus. Next, we have something called disseminated intravascular coagulation. It goes by DIC. What happens here is you just have clots and thrombuses forming. You have blood clots forming all over your body. They're forming so quickly, your body, you're not going to be able to get rid of them. So widespread clotting throughout intact vessels. This will typically occur. This can occur with pregnancy, septicemia, or an incompatible blood transfusion. So what happens is you get this incompatible blood. It goes in your body. It spreads throughout your body, and your body recognizes it as not being your blood type. So it's not very happy. So it's going to form clots to try to gather those incompatible blood cells up to get rid of them. And then now we have clots all over, and it's a big issue. So once again, with our red blood cells, they're going to be there to transport gases, and they're going to be there to transport oxygen to tissues and take carbon dioxide away from tissues. On the surface of them, they have agglutinogens, which are called antigens. The importance of them are going to be they're important for blood types. They act as markers to identify to your body, hey, to identify to your body, hi, I belong to you, I am this type of cell, I am a blood cell. There are over 15 known antigen systems in the body, okay, and we're going to have our ABO blood typing, and these are going to be the most important ones for our blood cells. So with our blood cells, the types of blood you can have type A blood, you can have type B blood, or you can have type O blood. Type A blood will mean that you have, and you can also have type AB blood, sorry. Type A blood will mean that you have an A antigen on the surface. Type B blood would mean you have a B antigen on the surface. Type AB blood would be represented here. You have an A antigen and a B antigen on the surface. And type O blood would mean there's no A or B antigen on the surface. And all these antigens are just markers to identify to your body that this is this type of cell they are. I'm a blood cell, I'm type A blood. Next, when you get your positive or negative, if you are Rh positive, you have the Rh antigen present. If you're Rh negative, you do not. So this blood cell would represent an Rh positive, an AB positive blood cell. We have the A antigen, we have the B antigen, and we have the Rh antigen. So this would be AB positive. This would be A positive because it has the A antigen and Rh antigen. Oops. This would be B positive because it's B antigen and the Rh antigen. And this would be O positive. No A, no B, so it's O. And then Rh antigen. Just AB negative. There's no Rh antigen, so it would be negative. It's not present. A negative. There's no Rh antigen present here. And this is O negative. No A, no B, no Rh. This is the universal donor blood type. Why? There's no antigens on the surface. Your body can't identify it. It doesn't see it as being anything. It just sees it as being a blood cell. It doesn't care that it doesn't think it's good or bad or anything like that. With antibodies, with every antigen, there's going to be a specific antibody that can attack it and connect to it and interact with it. You have these preformed antibodies, agglutinins, that are present in your blood with your ABO blood typing. They will not match your individual's blood. With the Rh factor, you don't have those antibodies formed until you are exposed to it. So what do I mean? If I'm type A blood, A negative blood, I'm born with the A antigen on the surface of my blood cells. Therefore, I will not have antibodies against this in my plasma, otherwise it's going to cause issues. But I do have antibodies against the B antigen because it's not on the surface of my cell. So if you gave me a blood transfusion and there's B, and you give me type B blood, there's these B antigens, all of a sudden my body says, these don't belong, and it starts to form an attack against them. All right, here's AB. We have A antigens and B antigens. My body doesn't have either A antibodies or B antibodies. It doesn't really care about them. Okay. Transfusion reaction occurs if the donor's blood is attacked by the recipient's agglutinins. So you get agglutination and hemolysis. So here's what an antibody looks like. It's like a Y-shaped protein with two active sites. And what they can do is they can clump or agglutinate blood cells together. Agglutination is going to create a network of cross-linked cells, and it's usually going to be seen as clumping. So it's going to be clumping together of red blood cells, and it's going to be done by antibodies. We don't normally have antibodies against our own antigens. If we do, then we're going to have an autoimmune disorder. All right. So with agglutination, here this shows type A cells. This H would represent an antibody that would interact with them. So you see it would hook onto one red blood cell and then hook onto another. And then you could get a bunch of these clumping together. So what happens is they form a clot, or a clump, not clot. They form a clump. And then what you could have is you could have macrophage come on over and eat these up and get rid of them in large quantities. With our blood typing, you can have, the way you can type somebody's blood type is you could get anti-A anti-serum or anti-B anti-serum and anti-B anti-serum. And what you do, let me get a little pen out here, you get a little well like this, and it'll have 3 circles on it. 1, 2, 3. And it'll be like A, B, RH. So I have an unknown blood, so I put some drops of blood in here, I put some drops of blood in here, and I put some drops of blood in here. Next, I take anti-A anti-serum, which will have anti-A antibodies in it, and I put it in there. I put anti-B antibodies in here, and I put anti-RH antibodies in here. If I get clotting in this well, that means that there's A antigens present. So I know I have at least type A blood. Why? Because the anti-A antibodies will only interact with the A antigen. If I get clotting here, then I know I have AB blood. Why? Because the B antibodies interacted with the B antigens. No clotting here, then it'd be Rh negative. So I'd be AB negative. Both anti-A and anti-B antibodies are commercially available, and they're going to be using them to do blood typing. Okay, so this is a nice graphic to see here. So if I'm AB blood type, I will have A and B antigens on the surface of my red blood cells, and I will have no antibodies in my plasma. If I'm AB blood type, I can receive blood from A because I don't have antibodies against it. I can receive blood from B because I don't have antibodies against them, and I can receive blood from AB because that's my blood type. And I can also receive blood from type O people because theirs is going to be stealth. There's going to be no antigens on the surface of their blood, so my body won't go to fight it. If I'm B blood type, I have B antigen on the surface of my red blood cell, and I have anti-A antibodies floating around. So I can receive blood from B blood type because that's my blood type, or O because that doesn't have any antigens on its surface. If you try to give me A blood type, which is here, or AB, these A antibodies are going to interact with them and cause clumping. If I have A blood type, I'm going to have anti-B antibodies floating around in my plasma, and I'm going to have A antigens on the surface of my blood, so I can take blood from people who have type A or type O blood. Now if I'm O blood, I have no antigens. I can donate my blood to anybody, but I can only take blood from people with type O blood because I have anti-A and anti-B antibodies floating around in my blood. So this would show somebody with type AB blood because there's clotting in both wells, in the anti-A and anti-B well. This would show somebody with type B because there's only clotting when it interacted with the B serum. This is type A because there's only clotting when it interacted with the type A serum. This would be O blood. There's no clotting that occurred. Okay, with blood tests, you can use them for visual properties, so there can be anemias or heart disease. You can do a differential white blood count to see what type of infection you're having. Do you have a bacterial infection, or do you have a viral infection? Are you having an allergic response? What's going on? We can check prothrombin time to see how your hemostasis system is working. Can you stop blood flow if you get an injury? And then we get like a chem profile, which does basically an overall blood chemistry. It checks out all the blood. It checks out many of the chemical levels in your blood. And then you get a CBC, complete blood count. It will count the formed elements, the hematocrit, and it will check out the hemoglobin for its size and content. That's it.